Welcome to the first colloquium for the spring semester. Today's speaker is Sauleh Siddiqui from the Department of Environmental Science. And I will let Jeff make the introduction.
Okay, so thank you, Aleka. So Sauleh Siddiqui is Associate Professor in Environmental Science, just joined AU this year. He also has an affiliate position with our department, and he's also a research fellow at the German Economic Research Institute in Berlin. He got his undergraduate degree in mathematics and public policy from Franklin and Marshall College, and his PhD in applied math and statistics and scientific computation from our neighbors in College Park. His primary interest, the area of research is in mathematical optimization and operations research applied to environmental systems, including energy infrastructure, food systems, and human health. And today he's going to be speaking to us on a bilevel optimization method for an exact solution to equilibrium problems with binary variables.
Great. Thanks, Jeff, and thanks everyone for taking time out this afternoon. I know it's always difficult with seminars and with everything else that's going on, so I really appreciate it. I'm going to share my screen. I am incredibly excited to be here, primarily because one, thank you all for inviting me into your department and letting me have an affiliate appointment, but also because my PhD, as Jeff mentioned, was in applied math, so I'm always very excited to be affiliated with the math department of whichever university I'm at. But also, hopefully, I'm looking forward to working with you all and seeing how I can contribute to the department in different ways. So today, I thought I'd give a little introduction on bilevel optimization, and then show its application to a very specific type of problem, which is a method for finding equilibrium solutions when the equilibrium problems have binary variables. So I'll proceed with that. So just to give you a little bit of background of the type of research I do, my research is basically based on thinking about how humans interact with environmental systems and how that function and outcome. So I like to think of how we make decisions in these systems can be represented as different mathematical problems, primarily optimization problems, because these decisions happen at a scale where you can model them as optimization problems, and then see how we can combine those different types of problems to understand what happens in these different systems. So this, you can kind of see sort of a sketch of an energy system, how it might work in terms of like the production of energy, the trade of energy through pipelines or ships, and then the storage and generation of energy, and then eventually as it might come to us. So this is the kind of research that I started off with, and the kind of research that this optimization and equilibrium problems usually get applied to quite a bit. So you can represent each of these. Let me see if I can. Okay, well, I think you all can see my mouse. So I'm going to try and do it through that. But you can sort of see that each of these little boxes or arrows you can represent through an optimization problem. And then the question then is, how do you computationally combine those optimization problems in order to develop outcomes in systems like this? So I've worked a lot in energy. I've also worked a lot in food systems. So you can kind of see that food has a similar type of sort of flow mechanism where there's certain activities that you can represent through different decision-making problems. And then there's connections between them of how the food moves around. Food is much more complicated than energy. I can pretty much tell you where some of the electrons are bumping in from to tell you where our energy is being generated right now. If you open up a can of tomatoes right now, I won't be able to tell you all the places that it's been. So because these can get very complex, you sort of need techniques to be able to handle some of these things. Of course, when thinking about food and energy connections, I also work in human health, because some of the impacts from food systems, but also energy systems, particularly through climate change, human health systems are also impacted. So I do a lot of work in those areas as well. And I like to see how we can apply some of the techniques that we've developed in energy and food systems and apply them to different areas of health as well. The thing that really complicates all these systems is the fact that we make decisions in a certain way, and specifically, so I don't really work on individual level decisions, but I really like to think about how we as aggregate humans, so as organizations, as companies, as states, in state levels in the United States, how do we make decisions and how do our decisions influence what happens in these differences? So a lot of what I'm going to present today is talking about how you can take traditional mathematical optimization and apply it to different types of systems. And I'm going to show you a specific example from power systems on how we can modify it and then how computationally we can solve the problem. So moving from some of this inspiration, here's the mathematical formulation of a bilevel optimization problem. You're trying to minimize or maximize a certain function. So that's that function f. And so a traditional optimization problem is just these two first lines here. You minimize a particular function and then subject to certain constraints. So these constraints, you can write them as less than or equal to or inequality or equality constraints. Because of the previous diagram that I showed you, a lot of times the decisions we made aren't really just constrained by functions. They're often constrained by other decisions. For example, if I decide to produce electricity in a particular state, then that is constrained by what the decision of the natural gas producer is in that state for how much they're going to sell me their natural gas for. So often in these types of systems, instead of just having single level optimization problems, you have this bi-level structure where you want to minimize a certain objective, you have constraints there, but then you're also constrained by other decisions. So in this case, the upper level problem here, the decision variables are signified just by, the decision vector variables signified by x, and then the lower level variables are signified by x bar I. And you can have more than one lower level problem. So you can be constrained by multiple different types of optimization problems. And so then the goal here is how do we take these problems, one, and formulate them to represent the systems? That's one topic of research. The other topic of research is also how do we actually then solve these problems? So how do we efficiently compute solutions to these problems that show up? I'll pause and see if anyone has any questions about the formulation that I'm sort of showing over here. So I've shown this formulation pretty much as sort of general functions right now. Generally, these problems are solved for continuous cases because it often becomes difficult to sort of think about binary variables. But that's one of the things we'll talk about today. When instead of continuous variables, if you had binary variables or integer variables, how you could go about solving these types.
So, quick question about the bar. Is
Sure.
that so? X and xi. Xi is in a given subspace, and what's the significance of the bar?
The significance of the bar is that in this slide, I'm using the bar to denote any of the lower level problems. So any of the decisions that happen at the lower level. So any of the decisions that are constraining other decisions, those are signified by bars. So you'll see the xi bars, they're all at the bottom. But that's a good question because you'll see in the upper level problem, the xi bar appears in the objective function, but it doesn't appear in the constraints g and x. And that's mostly just to get away from some economic ideas about games and not get us into trouble about being our constraints being dependent on other people's decisions. Usually what happens is our sort of objectives or profits are dependent on what other people do, but we're usually constrained by our own sort of internal decisions. So you can have those xi bars inside the constraints too, but just to keep life simple, I've kept it only in the objective functions.
Thank you.
Of course, please interrupt me anytime. That was useful. Okay. Great. So so moving on, right? So how do we solve these things, right? So how do we computationally deal with an optimization problem inside another optimization problem? Usually you solve general optimization problems through either gradient-based methods, so where you use some Newton-based method type technique to try and understand where that function is minimized. And there's a host of techniques to do this for continuous variables. So that's one option. The other option is using some evolutionary algorithm, so like genetic algorithms or simulated annealing or something else like that. Both of those things are very difficult to apply to these problems, primarily because if you try and take any gradients of the upper level objective, it's difficult to understand how you would consider the lower level decision when taking those gradients. So that gets a little difficult. And in the simulation, the population-based methods, the problem is that these problems get really big, and those methods are often, you don't know if you're solving it to optimality. You also don't know if they're going to work the same way each time. So you might get a different solution each time. So what usually happens is that you take this lower level problem and through its optimality or Karush-Kuhn-Tucker conditions. For those of you that don't know what these are, essentially it's like taking a first derivative of a function and setting it equal to 0 to try and find optimal values. And so of course that only works if your f bar I is, for example, is convex, and usually your g bar I and h bar I need other conditions, but usually if both of those are linear or affine, that's fine. So there are certain conditions under which this works. And whenever those conditions are there, what you can do is you can convert this into a single level optimization problem. And so what you'll notice is I've replaced the lower level problem with some vector valued functions over here, given by capital G and capital H. And the way you can formulate this through KKT conditions is that those functions have to be non-negative, and the pairwise product of those vector valued functions has to be 0. So that's the perpendicular operator, just indicating that for each element of capital G and each element of capital H, when you take the product, that product needs to be 0. Again, that comes directly from the similar thing of taking a first derivative of the Lagrangian function of the lower level optimization problem. So we've kind of taken our old computational problem of having a problem constrained by another optimization into this new one where we have this perpendicular operator. Those of you that are kind of well versed with optimization, you know that every time you're sort of multiplying two constraints together, this can get very, very complicated, and to both guarantee optimality but also computationally solve something like this. So there's two tricks people use. One is you can replace this perpendicular operator with disjunctive constraints, which means you add certain binary variables. So for example, in this case, I pick a really big constant m, and I add a vector of binary variables b. And I'm being a little crude with the notation here, but this is just to show the idea that, if b is 1, then the element of capital G will be forced to be 0, and the element of capital H can be as large as you make m. And then if b is 0, then it's the other way around. So it forces one of capital G or one of capital H to be 0. And these are usually the standard way that people have solved these. The problem is when you introduce binary variables, these optimization problems are also difficult to solve. And the other problem is you don't know what your capital M is. You're artificially constraining your problem by doing this technique. The other option is to use some nonlinear optimization technique, and that essentially means that instead of that perpendicular operator, we can use a Hadamard product. And so again, the pairwise product of capital G and capital H has to be equal to 0. Since they're both non-negative, you can replace this with a number of different types of products, and you'll be fine. And the problem with this one though is because this is non-convex and this is nonlinear, you're not guaranteed locally. Sometimes you're not even guaranteed locally optimal solutions, and globally optimal is definitely out of the question in trying to prove that this happens. But the nice thing is that this is very, very quick. So you can actually solve pretty large instances of these problems by using this nonlinear technique. So this was just meant to give everyone an introduction to bilevel optimization problems, and show you just some tricks of solving them. So one of my areas of research is trying to understand how we can create better nonlinear optimization techniques that can solve these problems more efficiently. And I use these quite a bit in different scenarios. So especially when we're thinking about endogenous decisions. So whenever our decisions are endogenous to the problem, where they can change depending on what we do, those are cases where these bilevel problems show up quite a bit. So the standard place is sort of setting policy, different types of policies. For example, if I want to set any type of carbon emission policy, I'm trying to set either a tax or a cap and trade policy so that the market reacts in the right way that I want it to. So the market reacts in a way which is optimal for everyone, but also beneficial for reducing the emissions as well. So there's this kind of trade-off that happens here, and you can use bilevel optimization to form this. The other places that I'm currently using this is tuning the hyperparameters in machine learning models. So, at the base, every machine learning model is essentially an optimization problem when you're trying to make it learn and figuring out parameters. But there's certain hyperparameters in machine learning problems. So for those of you that know these problems, an example is the C parameter in support vector machines, which influences how your vectors are drawn to divide up your data. So usually these hyperparameters are picked arbitrarily, or there's sort of a, there's a process sometimes to pick these, but there's no formal way to understand what the best value of these hyperparameters are. So what you can do is you can think about minimizing some loss function, or you can think about some performance measure that chooses the hyperparameter at the upper level, and then the lower level produces sort of a learning model that helps you learn in different ways. So this is part of 2 NSF awards that we're working on right now, into thinking about how do we tune these hyperparameters to improve machine learning model performance. And the other place we're using this is thinking about data generation. So thinking about where different infrastructures intersect. How do we understand the intersecting data between those infrastructures? So over here, for example, if you look at the blue colored boxes, they think of those as representing one particular infrastructure. In our example, it's energy infrastructure, for example, the production, consumption, transportation of energy. And then the orange boxes represent, for example, production, consumption, and transport of food. These are related at different points. So, you use energy in your food system, but also your food system is responsible for providing energy at certain times. So I can represent those kind of with this vector valued C. And the idea is that if I minimize over C and my decisions in these individual systems, if I can minimize the expected value of the differences between the two, I can figure out what C needs to be in order to understand that these systems work together. So we know a lot nowadays about our individual infrastructure systems, but we know very little about how they're related. So that's another project that I'm currently working on to try and understand how we can use this. But that's sort of a general overview. And so you'll see bilevel optimization problems applied in all these places. Today, though, I'm going to talk about a very specific type of problem, and that happens in electricity markets. So electricity is a very interesting product, as you all know, and it's very it's important for us now as we go forward in this world of climate change and emissions to understand how our system works and understand how we can make it better. So in general, the biggest thing about electricity that separates it from any other product is that it needs to be instantaneously produced and instantaneously consumed. We have some storage right now in the electricity system, but the majority of electricity that we're consuming is actually produced at the same instant that we're consuming. So electricity systems really involve a lot of prediction, of course, because we need to know what's going on, but you also need to design your market and you need to design your system so that something like this can operate in an efficient way. The thing I like to tell everyone is if you don't think about the system quite a bit, it means it's working perfectly. So we don't think about our electricity system, but if we stop and ponder that it's something that just works most of the time. I know it's getting worse and we have to think about how to make it better. But because it works most of the time, you have to realize that there's lots of different math behind how the electricity system is producing our electricity and making sure that we consume it as well. And so I can focus on a lot of the different math that happens in the electricity market, but the one I'm going to focus on is the role that a system operator in a wholesale electricity market plays. And what the system operator does, and you might have heard of them, they're, the one that is sort of north of us is called PJM, so Pennsylvania, Jersey, Maryland. And that's also one that influences kind of what happens in DC as well. And there are other ones that make different decisions. But essentially what they do is they create market mechanisms where they plan on buying electricity from generators and they plan on selling it to utilities, essentially, that the people that supply us, right? And they have to play a balancing act, literally, because they have to balance the electricity bought and the electricity sold, and they have to set prices in markets like this. So they have to understand what the different prices are for buying and selling electricity. The system operators are actually nonprofit entities that are created by the government, because the idea is you can't have a profit-making entity in the middle of this electricity market, because then they would really hold all of us hostage and try and make sure that we pay more electricity bills. So they're in this weird situation where they have to make sure that everyone stays happy. And in fact, one of the things they do is sometimes they have to tell generators to do certain things for our benefit. An example is if sometimes a really expensive generator is operating and it's profitable for them to operate, sometimes they have to tell that generator to shut down because they would either drive electricity prices up, or they could, change some emission standards that we have to control. And in telling that generator to shut down, sometimes they even have to pay that generator money in order for them to shut down. So that's where some of this game theoretic aspect comes in, that you have generators being paid to shut down. Sometimes you have to pay generators to stay shut as well, because there's too much electricity in the market. So especially in terms of when you have a lot of solar and wind in the system, sometimes you have to tell generators, please don't turn on, even if they want to. And because they say that we might make some profit, you have to actually pay them to shut down. And those are called compensation payments in electricity markets. So I know this can get very complicated very quickly. So let me pause for a second and see again if anyone has any questions about kind of the system operator's role or stuff that I'm talking about over here.
I guess I'm the question person today,
Yeah.
but one interesting thing happens with energy is that there's times at which we have an abundance of energy, and there's times at which we have a need for greater energy. And I've heard of all these techniques of, say, for example, using the excess energy to pump water into some sort of, when they design a system like this and your economic system, is that kind of built into the system and that's part of the computations?
Yeah, so storage systems like that, so pumped hydro or like hydro storage systems that like you described, those are usually built in, right? The harder part is because there are not so many of them, you don't really know how to value them, right? So what's the value of selling a pumped hydro extra electricity, right? And a lot of times in California, electricity is now taking negative prices, which means that they're actually paying people to consume electricity quite a bit of the time. Because we have so much of it, right? So, but you can't charge that negative. You can give a storage that negative price, but the storage would usually want a better price, right? Because they're like, well, I can actually sell this back to you later. So they're actually figuring that stuff out right now on how do we actually value stuff like that. But you're absolutely right. This is a big problem, and actually, it's a big mathematical problem too, because it's a big valuation problem to understand what the real value of storage is in our future system.
Yeah, and it's complicated too, because you never quite know, quote unquote, what the future is, because it's weather dependent and all sorts of other things. So
absolutely. Yep.
Excellent. Thank you.
No, of course. Other questions? Please keep being the question person, because I think that helps me as well. So okay, so thinking about how the system operator then makes a decision, right? And there's actually been quite a bit of improvement. So mathematicians have done a lot to help our electricity system. So they were just using linear programs, which means all the objective function and constraint functions were all linear. But as you can tell, electricity systems have a lot of integer decisions. And by integer decisions, I mean, turning on a power plant costs money, and also turning off a power plant costs money. And those are essentially yes, no decisions instead of continuous decisions. You can't really operate a power plant. There's sort of minimum operating and maximum operating constraints that go into power plants that make this an integer problem as opposed to a continuous problem. So for over the last decade, they've actually started shifting from linear to mixed integer, and they've actually saved a lot of money. So in 2004, PJM implemented its mixed integer program in its day-ahead market, and they estimated just by shifting from linear programs to mixed integer programs for their operations, they saved about $100 million a year just by that small savings. And then in California ISO, they estimated that they were saving about $52 million per year just by using mixed integer programs. Just to give everyone an idea, I mean, linear programs have been around for decades now, and mixed integer programs, the type that these ISOs solve, have been around since the 1970s. And we have the computational capability to solve these. I was actually talking to some ISO operators. I'm like, oh, do you have like these huge supercomputers running that solve these mixed integer programs? And up until about, I'd say, 2014, they were literally just solving this on a laptop. So there's a huge opportunity over here for us to keep advancing this and actually developing new techniques here that can then be translated into these system operators. So optimization is a ripe field right now, especially in the energy sector, because of these problems. So this is just the citation for where some of these things came from. So, all right. And so here's how they do it currently. And I'll tell you what the problem is in doing it like this. So if you have a mixed integer program, you still have to price it somehow. And the way they price it is through these marginal prices that come from constraints. And for those of you that don't know optimization, what happens is whenever you solve an optimization problem, there are dual variables attached to each of your constraints. And what those tell you is they tell you the cost of relaxing that constraint. So they tell you, if I relax this constraint by 1 unit, how much better can I do? And those are really how electricity markets are priced nowadays. They price it through those dual variables in optimization problems. And so because they price it like that, like I said, generators sometimes can earn negative profits because of the way market clearing works. And again, this is coming all from the optimization problems. And so what they need to do is sometimes they might either leave the market, which we don't want them to do. We want them to keep generating electricity, even if they're not making a profit, or they don't follow the schedule that the ISO has told them. So the system operator would tell them, this is when you generate, and they might be like, no, I'm losing money that way, so I'm going to do something else. So when you have non-convexities and indivisibilities, again, when you have these integer decisions, using duals as market clearing prices doesn't quite work, right? And the simplest explanation for that is that you can't take a derivative of a discrete function. I mean, you can, but really, like the way that they're taking derivatives, you really can't. They're assuming these problems are continuous, and they're taking derivatives to try and get prices. And they've actually proven that these prices can clear the market. So, so there's papers out there that show that you can take a derivative and this will work, but mathematically it's actually wrong. And I'll show you a perfectly simple example for where it's wrong. So what ends up happening in these markets is that the system operator pays out a lot of compensation payments to them because they're calculating prices through these derivatives that aren't correct. And so it clears the market, but then it also results in sort of a lot of what we like to call incentive incompatibilities. And so you have to pay them some money to make up for the profits that they're losing out on. And so there's a lot of sort of game theory aspects of this that show up quite a bit as well when you price and you design markets like this. So just a quick introduction to continuous optimization problems. So how do these markets work, right? So if I have an optimization problem, again, I can take Kruskun-Tucker conditions or first derivatives, and I can write it as a complementarity problem. If I have many optimization problems, so I have many different generators here, right? So think of each of these generators as making a decision about how much electricity I can produce. The nice thing is I can take the same Kruskun-Tucker conditions, stack them all together, and then solve them as complementarity problems. And essentially, this is one way of handling continuous equilibrium problems. If I just had continuous decisions, we can actually solve those pretty well. We essentially take first derivatives, set them equal to 0. They're a little bit more complicated because they look like this, but we can solve those things, right? So this is essentially how they're solved. However, when you have binary decisions, you can't really take derivatives like this. And so there exists no scalable approach to find Nash equilibria with binary decisions. So either what current approaches do, they ignore the gaming aspect. So they assume that there's no gaming aspects at all. They just combine all the optimization problems into one. They commute all permutations of the binary variables. So they just say, like, let's just check everything and see what the answer is. That's quickly beyond the bounds of computational tractability. They use a two-stage approach, and this is actually what markets do right now, and I'll talk a little bit about this, where they first solve it as an integer problem, then they fix the integer variables and they resolve it as a continuous problem, and they can get prices like that. So that's another way to do it. And then the other thing is you can relax or linearize the binary variables, apply equilibrium method. So you can assume the binary variables are really continuous, kind of solve the problem, but this doesn't really work. And I can say it doesn't work because I was on this paper. So it's okay for me to criticize this particular one. So you can solve it and you can solve really large problems and you get approximate solutions, but you're not really clear what that solution is. You know, most of the time you can computationally say it's a good enough solution, but you don't know what it really is. So you have all these ways people do it. So we're going to present a new way of doing this. And the way that we used to do it is you kind of take this problem and then you basically take derivatives, right? So over here, I have this problem. Lambda over here is the dual attached to the constraint. And so you can think of this as the first order condition with respect to the Lagrangian function. And so this is what KKT conditions look like. For those of you that haven't seen these before, is essentially you're sort of taking sort of the partial derivative of this vector with respect to each of the vector variables xi, and then you have a dual times the derivative of the constraint function as well. And then again, as with Lagrangians, this has to equal to 0, and then this is the complementarity condition where either you're unconstrained, so you're not hitting the constraint, in which case lambda must be 0. So lambda is your dual variable or your price here. Or if you're hitting a constraint, then lambda can take on a positive value, and that lambda tells you if you were to relax this constraint by 1 unit, how much would your objective function improve by? So what the original paper did was we took a derivative with respect to y, which is a continuous variable. Sorry, this isn't showing up here, but you take a derivative with respect to your continuous vector, but you also take a derivative with respect to your binary vector, which again is not correct. And I'll show you why it's not correct. So you can't take a derivative with respect to a binary vector. And so what we're going to do is we're going to propose something different. We're going to say, instead of taking a derivative of a binary vector, derive KKT conditions. So derive those conditions for both states of each binary variable. So derive it for the 0 state, which is, think of it as a power plant that's shut off, and derive it for the 1 state. So what we're doing is, instead of trying to compute what happens under both conditions, we're saying derive the constraints that we can use for both of those conditions. And then we add an objective function on top that can help us pick an equilibrium. And then we include compensation payments to ensure incentive compatibility. So we're still going to compensate people for turning off or turning on, like happens. But what we're hoping is that our method can yield sort of better solutions than exist right now. This is just the map, by the way. So I don't expect you to understand all of these slides. This is just where we're going. Is that
Just a quick question here.
Yes,
so,
go ahead.
So how many binary variables do you typically have?
Oh, that's a great question. So I will talk about that in a little bit. But typically what you have is, for each sort of power generator, you have about 4 or 5 binary variables. And then depending on how many power generators you have, that problem can get very, very big. So usually you're thinking about in thousands of what you're trying to solve in terms of binary variables, at least. So, but it's not in the millions. So it's not, completely out of reach, but you're still in the thousands.
But if you have, n binary variables, then that means 2 to the n states that they could be in. So does that actually mean 2 to the n problems you need to solve here?
So in our case, what happens is it doesn't matter if we have many generators, because what we really care about is how many binary variables are for each generator, right? So if each generator has 5, I just need 2 to the n, which is 32 different conditions. And then I just 32 plus 32 plus 32.
I see.
But in traditional conditions, you would need all the binary variables. You're right. Good, great question. Perfect. Okay, so here's what we're going to do. So the reformulated problem is actually a multi-objective bi-level optimization problem. So you notice that this isn't really a bi-level structure. But what I'm trying to do in this case is that I'm trying to say, like, my objective function will help me pick which solution I'm going to pick. And so my upper level in this case is picking an equilibrium for my electricity market, and my lower level is changing depending on how I'm picking it. So this is the map, but let me tell you a little bit about how it's done right now. So the way it's done right now is we can think about how they get prices for integer programs right now, and how they get different types of dual variables. So the way they do it right now is, imagine this is my optimization problem. So simple quadratic function, x minus 0.5 squared, and my x is a binary variable. So it can either be 0 or 1. And I'm trying to minimize my objective function, right? The solution to this problem, if f can only be 0 or 1, is either 0 or either 1. Now, if you put this in any numerical solver, or you use any of our electricity system people right now, what they do is, the way they solve this problem is they'll solve it, and then they'll fix the value of x they got, and they'll resolve it as a linear program. So they're actually able to get dual variables and prices for this. So if I solve this right now, again, I'll get 0 or 0.5, and then I'll get a dual variable in the standard method that is the slope attached to that point, right? So for example, if I solve it and my computer gives me x equals 0, I'll actually get a dual variable that slopes down, which will mean that my dual variable will inform me that, oh, I can actually get a better answer because it's sloping down and I'm minimizing my objective. But in fact, I can't, right? Because the only other option is x equals 1. So really what I really want is my dual variable to be 0, because I can't really improve with my other option. But because I'm solving this like a continuous problem and calculating the slope at this line, it looks like I can do better. And so this is what's happening nowadays, is if you use this technique, you're generating prices through these slopes. And so it looks like you can do better, but you really can't. And so you compensate people based on those slopes that you're calculating from discrete variables. So this is the proposed approach. So Dick O'Neill et al. In 2005, they published this paper, which is now being used. So what they do is they solve the mixed integer program using standard method, and then they solve the linearized problem. So you solve this problem, and notice x is a binary variable here. You solve that as a mixed integer program, and then you fix your x to whatever solution you got. Now that you have these equality constraints, you can attach a dual to those constraints, which is the mu. And remember, mu is that slope that I was telling you about that's calculated. And then you can actually solve this problem. And this is how we generate, this mu is essentially, mu and lambda are how we generate our electricity prices today. This is how all the prices that happen right now in electricity get generated at the system operator level. And in fact, this is a really good paper. I actually recommend for those of you that are interested to read this, because what they show is that you can actually clear the market with these prices. So these prices are economically okay. So according to economics, these prices are okay. They might be wrong, but they're okay. They're okay because they clear the market. So you can still sustain a market with them. Your market might have bad incentives in it, but it'll still work, which is why they use it. So we're proposing something different, right? So we're saying, let's try and figure out if there's a better way of doing this. And again, these aren't the correct prices, right? That's not the correct prices that are generated for this. So here's what we do. Instead of relaxing the binary variables, we think about something called a switch value, right? And essentially what it is it's the difference of the objective function value had you chosen 1 or had you chosen 0. So again, back to your question, Jeff, depending on how many binary variables you have, again, this can sort of increase exponentially. But again, if the individual optimization has a few binary variables, which is the condition we're in, you only get added constraints for those particular types of ones. So we want to look at the difference between choosing 1, for example, and choosing 0. And not only does our binary decision change, but our associated continuous decision. So the binary decision can be turn off or turn on a power plant. And Y over here is our continuous decision, which is at what level does it operate. And so that also changes. So we need to figure out what the difference is between these two. And we call that difference kappa. So kappa is the difference between turning on and turning off. And we endogenously need to decide what these continuous variables are at the same time. And then again, using the simple example, in this case, kappa would then come out to be 0, right? So instead of using the slope to calculate the difference between the slope to calculate the prices of switching our decision, we're using this value of kappa over here. And that's the difference between these two functional values. So far, this again seems like, okay, this can get computationally very, very difficult, right? So this is where the technique really comes in. Like, how do you formulate this so that you can actually solve it for a reasonable size problem and actually get a solution that's understandable? And so we actually advocate for this switch variable to be interpreted as a shadow price for optimization problems with binary variables. And actually, Jalebi and Fuller have used sort of this concept from us, and they've sort of also interpreted it as a measure of disequilibrium, because you can kind of also think about it as like, if I'm turning on and turning off, often it's hard to find an equilibrium under those conditions. So the larger this switch value is, the more sort of disequilibrium condition you're in as well. So thinking about this binary game, so let's define our game now. So if we have a set of players, each seeking to solve a binary problem, again, it's an objective with certain constraints. An equilibrium in a binary game is basically a vector of continuous and binary variables such that no player is better off than where they are right now. So it's the standard definition of a Nash equilibrium, which is essentially that each player does not want to deviate from what their conditions are. So if you tell each player, this is the equilibrium values for you, and this is the equilibrium values for everyone else, you calculate your objectives and you say, I don't have any incentive to deviate, so I'm going to stick with what I am. So that's the standard definition of a Nash equilibrium in this case. But in binary games, often these don't exist, right? So the existence of Nash equilibria comes from the fact that your profit functions are continuous, and you essentially try and figure out where those intersect. or your reaction functions, excuse me, are continuous, so you try and figure out where they intersect. But if your functions are continuous, often in a lot of cases, these don't exist. And you get cases where, the equilibrium is sort of people turning on and off with a certain probability. So we define a different equilibrium. We define a quasi-equilibrium in a binary game with compensation. And we say a Nash quasi-equilibrium in binary variables is a feasible vector in which you still compare if you want to deviate, but we give you a set of compensation payments, right? And so we say that instead of like not deviating, we're gonna give you a certain amount of payment, and then that's gonna ensure that you don't deviate. Now, by construction, there's always an equilibrium in this, right? I can give everyone $1 million and they're not going to want to deviate from whatever solution they are. So the key here is, how do we come up with an equilibrium where this particular compensation payment over here is minimal? So we want to pay the minimal amount to make sure that the equilibrium holds. And that's going to be the goal of our work. How do we figure out the minimal amount of payment to keep people where they are in equilibrium? Any questions about Nash and equilibrium and compensation payments?
Quick question on the quasi-equilibrium. Does that always exist?
Yes. So so it always exists. Like I said, the solution that's not interesting always exists, where I can make my compensation payments. And I always forget this Greek variable. I've given this presentation so many times. I think it's a C, or it's a zeta, for someone who knows Greek variables better than me.
That's zeta.
Yeah, that's a zeta. So
C has a little more of a squiggly in it. I use those a lot in complex variables.
Nice. So yeah, so my zetas, if I make my zetas really large, an equilibrium always exists.
Right.
But the hard part is showing if an equilibrium exists for a minimal value.
Right.
So,
that's what I meant. Does that minimum always exist?
yes. So the minimum does always exist. That we actually prove in the paper. So we actually prove in the paper that it exists, and we prove it by construction, because you can find it with our method on what it would be.
Thank you.
Of course. So then moving on from this definition. So if we assume the KKT conditions are necessary and sufficient with respect to the continuous variables, so essentially those are some convexity assumptions we make, we can compute the optimal response for both states of the variable xi. So we can compute what will happen if it's 1. And again, this 1 isn't a vector because I know that this will be, again, 2 to the n different combinations, but I've done it so that it's simplified for us. So we can compute the optimality conditions for when it's 1, and we can also compute for when it's 0. Right. And by the way, we have to compute both. So we have to compute what the binary variable will take, but also what the continuous response will be for the particular decision of our binary variable. And then we check which strategy is optimal by comparing payoffs. So this is where the bilevel comes in. So our upper level objective helps us compare these two. Like, is it more profitable to turn on, or is it more profitable to turn off? And we can actually use some if-then conditions over here. We need some if-then conditions to say, like, okay, if it's more profitable to turn on, because we're minimizing, then pick 1. If it's more profitable to turn off, then pick 0. And if we're indifferent between turning on and turning off, then it doesn't matter. Let the optimization pick whatever it wants. And so we use the switch value to add constraints that look like this. And so you'll notice that these constraints, and essentially this is where we sort of get into sort of mixing our computation, our math, and our economics here. So we say the profit you make by turning on plus any switch value that you would have by turning on minus any compensation payments you receive, because again, we're minimizing, should be equal to the same condition if you had turned off. So I can move these both to this side, and then you'll notice that this is essentially saying me turning on plus any switch value minus any compensation payments should be equal to the decision of me turning off plus any switch value minus any compensation payments. So our switch value helps us compare these two. And then again, I have the traditional sort of binary disjunctive constraints here. So again, x can be 0 or 1. And I pick a large K because what I want is I either want me to be turned on or I want me to be turned off. And when I'm turned on, so when x is 1, I want a switch value and a compensation payment computed for when I'm on. And when I'm off, I wanted the switch value and a compensation payment computed for when I'm off. And again, these are all continuous variables over here. So I'm trying to let the optimization decide when I want to turn on and turn off. And I'm trying to let the optimization decide what my switch value and my compensation payment would be. So we introduce another additional player, which is essentially the market operator in this condition. And the upper level player optimizes some function f and a function g of the compensation payments. So the function f can be some measure of social welfare. So you can think about it as consumer surplus or producer profit and add all those together. We didn't define those because depending on where we present this takes different values. If you present this in the United States, this f is exclusively made up of generators and private companies. If you present it in Europe, they really care about social welfare and consumer surplus as well. So f can be many different values. And then a function g of the compensation payments, right? This function g can be as simple as adding up all the compensation payments. So essentially what we're trying to say is you're trying to pick between getting really good outcomes for your market and how much compensation payments are you going to give to the market. So you don't want to pay a lot because that's bad, but you also want to make sure that everyone's happy. So sometimes you have to pay to make sure that we get prices in electricity that make sense. And so we guarantee feasibility, optimality, and incentive compatibility for each player. And so the nice thing is this player can effectively consider the trade-off between market efficiency and compensation payments. And this is something we couldn't do before. So what the Bilevel allows us to do is it allows us to have an upper level player that can help us do the trade-offs between market efficiency and compensation payments. And then the lower level can resolve the market and help us get prices and other values. So what does this look like mathematically? I know this is a lot, but I figured if any department can handle it, it's this one, right? So if I look at this optimization, this is essentially what we're solving now. So we're solving this big optimization problem. It has my multi-objective objective function right there. It has an optimal decision for each player I, given that they're choosing to turn on. So again, these are indexed by index I over here. So these will be included for each player. And again, for each index, there's going to be 2 to the n combinations of these. You're going to have a set of constraints that are optimizational yi for each player I, given that they're turning off. So you'll have those in there. You have this comparison of payoff. So this is really where you compare the objective functions from turning off and turning off for each player. And then you have a translation mechanism for individually optimal strategy of an equilibrium outcome. So what we're hoping is, we're not hoping, what we prove is that if you solve this problem, you can actually guarantee to get an equilibrium. And so I'll show you some of those results right now. I'm not going to go through the proofs of these, but essentially what you can show is that any feasible solution to the previous problem is a quasi-equilibrium in a binary equilibrium problem. So any feasible solution we get to the previous problem, that'll be a quasi-binary equilibrium. However, if under certain conditions, we can write this as a linear or quadratic mixed binary program. And those conditions aren't very harsh. They're better than the conditions used today. So they're essentially just saying we require some convexity in the objective function and linearity of constraints. And we require some other small conditions, but under sort of certain conditions, you can rewrite it as a linear or quadratic mixed binary program with linear constraints. And those we can actually solve quite a large instances of. So we can actually solve this for market operator level optimization problems. And again, these conditions hold for everything else where it's applicable for. So they hold for the uplift problem, hold for resource markets, agriculture, investment, games, all those other things. And so the other proof that we have is that we prove that we're always at least as good as the two-stage approach. And by at least as good, I mean that in terms of social welfare, however you define it. So we can clear markets and we can create prices that are better or always at least as good as what's done right now. And so what we're saying here is that we can actually guarantee, instead of them solving 2 different problems separately, we can guarantee that we do better off than them as well. So also under these conditions, we can guarantee that we can pick a minimal value for our compensation payment. So under all the market conditions, we can show that the minimal value exists, and we construct and we show that if you solve the problem, then you can actually calculate it as well. Okay, so I'm going to stop there and I'm going to go through an example to try and help everyone understand. I know there's about 10 minutes left, so I'm also cognizant of time, but I want to pause and see if anyone has any questions on the math before I kind of show how this works. Oh, and I'm sorry, I'm not monitoring the chat, but there's no questions in the chat either. Okay, great. So let me show you for a very simple example. So this is very, very simple, just to help us go through it. But essentially we have 9 generators, 6 nodes, 4 load units, and we're only using 2 periods to try and help you see what happens, right? So let me show you what happens. And we added a generator compared to our previous examples. And we're going to compare different market rule implementations. So we're going to compare the standard approach, like what happens now. And then we're going to compare 2 approaches from our side. One is a game theoretic solution, which is what we advocate for. So we say that you might not need to pay as much compensation payments to clear the market. And then the other one is one that's being considered right now, which is basically this idea. People get mad when you say you should pay generators for not turning on because it's hard for people to understand that, like, sometimes you have to pay for the greater good. But yeah, there's a framework in right now which says don't pay generators for doing nothing. They have to be doing something to pay them. But the way our market is set up, we have to sometimes pay them to do nothing. So we're going to test that policy as well and see what happens. So let me go through these solutions with you. And the best way to read this is from left to right. So first, the first 2 generators, you can forget them because they're not active in any case. So they remain turned off. So generator 3 to 9, initially, their generator 3 to 6 is turned on and generator 7 to 9 is turned off. In our standard approach, if we solve this problem, what happens is we tell generator 3 to turn off. Because generator 3 turns off in this case, they actually lose money. So they would have made money if they stayed on, but because we wanted the market to clear according to our standard approach, they actually lose 300 in profit. So we actually have to pay them that 300. That's from the standard approach. Generator 4 is on. We ask them to stay on, but because of the way they operate, they actually still lose money. So we have to compensate for them. Generator 5 is on. They stay on. We tell them to stay on, and they make a profit, so we don't pay them any money. And similar for those other generators. So generator 7 was off. We asked them to turn on and remain on. Generator 9 is off. We asked them to remain off in the standard approach. So this is what it's done nowadays. And so you can see that you can make, this is what the generator profit is. This is what we've paid them, though, in compensation payments. The other payments are consumer surplus. So this is how better off the consumers are. So you can sort of add it up and you can see that while the total sort of surplus is 3,100, you have to pay the generators 460 in compensation payments. So, and again, this is where it gets into economics, and I'm not an economist. So economists like to separate the compensation payments from how well people are off. So I'm not going to comment too much about that, but you can sort of see, like, they don't want paying. One of the things that people don't want to do is pay a lot of compensation payments because that's seen as market manipulation. So you don't want to pay a lot of these, right? You get a certain amount of welfare. Now let's look at our game theoretic approach. In our game theoretic approach, generator 3 was on. They turned off, so they lost 300 in our case, but we only need to pay them 15. And the reason we only need to pay them 15 is that if they had stayed on, they would still lose money, but they would only lose 285. So what our model does is it endogenously figures out that if they're losing money, how much would they lose if they were on versus if they were off. So we don't need to pay them their entire losses. We just need to pay them enough so that they don't switch their decisions, is what we're saying, right? Generator 4 was on. We asked them to remain on. They actually lost more money in this case because you'll see we do something different. We only need to pay them 65. So we don't need to pay them for their entire loss. We only need to pay them 65. And that's something that comes out endogenously from our model. Generator 5 was on. They stayed on. They lost money. We won't need to pay them anything because they would have lost money anyways in our formulation. And you'll notice that generator 7 makes a lot of money, so does generator 8. And we actually asked generator 9 to turn on in this case. Generator 9 loses 5, and we compensate them for 5, because otherwise they would not have made any profit. In this case, they were off. So by adding generator 9, we kind of change how the market works. But what you can see, profits are lower. Consumers do better with 2120. Total surplus is lower, but you can see that we've reduced compensation payments by quite a bit using our game theoretic approach. And the no loss and active approach is interesting because this was interesting for us to show to policymakers, because one of the reasons they wanted this approach was they were like, we pay too much compensation payments, so we shouldn't be paying people if they're not doing anything. But what you'll notice happens in this case, and I think I don't want to, in the interest of time, I'm not going to go through each solution line by line. But what ends up happening is you actually end up paying more compensation payments because you're asking generator 3 to remain on. And because you ask them to remain on, you have to pay them extra money. And because you asked Generator 4 to actually turn off, they lost sort of one in there because they were on in the first period, you pay them money. And then generator 5, you have to pay them compensation payments as well. So this gives a slightly different solution, but you can see the welfare is lower and you have to pay a lot of, the compensation payments, 910. And you have to pay a lot of compensation payments as well. So sometimes like just looking at the policy might not actually be the best idea. You know, a policy designed to reduce compensation payments actually can result in more compensation payments just because of how these markets operate. So a quick note on, so I won't go over this because I think we sort of saw those comparisons. And again, in the interest of time, I don't want to take up everyone's time by too much, but just some computational idea over here. And I explained this a little bit with Jeff's initial question. You know, so the main challenge where this method won't work well is if in the individual optimization problems have too many binary variables. That's when this gets computationally tractable. So this will solve 100 problems with 5 binary variables each much easier than 5 problems with 100 binary variables each. So that's where the trade-off comes in. So you can't use this for everything, but you can use it in power markets where this type of structure is there. And so if you want to have an idea of how sort of computationally this scales up, you know, you can sort of see, you know, for our particular example, we solved it with about 122 binary variables was what we were looking for. But again, we've also solved this for an instance for ISO New England. So we've solved this at the ISO level as well. So we've shown that this can be applied to some of those types of problems as well. So with that, this is just a conclusionary slide just showing what we accomplished. So we developed a method to find exact solutions to binary equilibrium problems. And we introduced this term for quasi-equilibrium. And then we showed when the problem can be solved, and we constructed solutions that had minimal compensation payments. And then we can show that this could apply to different types of market rules. Our code in GAMS is publicly available, so if anyone wants to play around with it, they're more than welcome to. And I didn't know how many graduate students would show up today, but I had a slide looking for graduate students as RAs for different types of projects that I have. So if I don't know how many are here today, but if people are interested in funded projects related to optimization and or machine learning, so we're using it to build sort of systems models like I described, but also to improve prediction of machine learning models, please do send them my way. I'm more than happy and excited to work with students. But with that, that's it. And thank you all for listening. And again, thank you all for inviting me.
Thank you very much, Sauleh. Thank you.
Thank you.
Are there any more questions for Sauleh?
I wanted to thank you for an outstanding talk. I really enjoyed it. One thing is really interesting. Were you, did I hear correctly that you went from Franklin and Marshall in Lancaster to College Park?
Yes. And I'll tell you something even funnier. I actually born in Pakistan. So I actually went from Karachi, Pakistan to Franklin and Marshall, which was a shock. I didn't even know where Pennsylvania was.